So here's a quick summary of the unit. If you have two objects, one mass over here and another mass over there, and the distance between the centers of the mass is r, then we know that the force of gravity, F of g, equals g, the mass of the object on the left, the mass of the other object, divided by the distance between their centers squared. So this is called Newton's law of gravity, or universal law of gravity. And of course, g is just a constant, 6.67 times 10 to the negative 11, and that's in newtons meters squared per kilogram squared. So that works everywhere in the universe between any two objects. All right? Now, a special case of that is if you have a mass, big M, and you have a little mass, m, that's on its surface. And in that case, if you want to find the force of gravity, you could say that the force of gravity between the two objects is g, the big M here, times the little m divided by the distance between them squared. And this quantity right here we can call the local gravitational constant, g. All right? So if we do that, then the local gravitational constant, g, just equals big G times m divided by the radius of the planet squared, and then you can take that little g times m to find the force of gravity. But of course, this only works when you're on the surface of the planet. Okay, if you get it farther away from the surface, then it doesn't work anymore. To find the force, you've got to use that expression right there. Okay, so that was the force of gravity. Some other things that you need to know along the way is that for a sphere, the volume is proportional to the radius cubed. So doubling the radius of a planet actually makes its volume 8 times bigger. Not only that, but the mass of an object is equal to its density times its volume. So if you double the density of an object and the volume stays the same, then the mass will double. And you use those in relationships that ask you, if you have a planet the same density of Earth but twice the radius, what is the gravitational constant, g or something? So those are just little things that are helpful to know along the way. So that's universal gravity. Okay. From there, we asked, well, how much potential energy does an object have when it's trapped on a planet? So if you imagine a planet, so for example, Earth or something, and you have an object right here, that object right there is in a gravitational hole, okay? It's not free to move. You've got to add energy. You've got to do work to get it away from the planet. And so we sort of showed and talked a little bit about how you do this. The potential energy of this mass m at that point, due to the gravitational field, is minus g, big M, which is the mass of the planet, little m, which is the mass of the object, divided by r. So that's the potential energy. This, again, is an equation on your reference sheet. So that tells you the potential energy of an object there. And it's negative because it's in a hole, right? And you've got to add energy to get it free. So, again, there's a local approximation. If you are moving an object somewhere near the Earth and you're moving it from, the floor to the table or something, you're changing this amount by a tiny bit, then there's a local approximation you can use. So this is the local approximation. The local approximation is that the difference in gravitational energies between any two points close to the surface of the Earth is just m times g times delta y. So when we use this equation, we're assuming we are moving something, changing its height close to the surface of the Earth. All right? So that's a local approximation. In general, though, if you want to know how much work it takes to get a satellite from the Earth up into orbit, you've got to find the potential energy on Earth, you've got to find the potential energy on the orbit, and take the difference. Okay? This doesn't work when delta y is bigger than about a mile, and it doesn't work if you're not on the surface of the Earth or really close to it. Okay? The third thing we looked at was the fact that when an object is moving in a circle, it takes a force to make it move in a circle. And so the force that's necessary to make an object move in a circle is equal to the mass of the object times its acceleration when it's moving in a circle. And when it's moving in a circle, we call the acceleration the centripetal acceleration. And the centripetal acceleration is v squared over r, where v is the velocity of the object, r is the radius of the circle. And so if you multiply the centripetal acceleration by the mass, you get the centripetal force. So this is the force necessary to make an object move in a circle. Okay, if you have more force than that or less force than that, it will move and it will change directions, but it won't be a circle. So this has to be true for it to be a circle. All right, then we put all these ideas together in sort of the big idea, which is called orbital mechanics. So orbital mechanics asks, how do we describe the motion of one object orbiting another? So in general, we are going to consider a large object, capital M, and a small object, little m, which is orbiting the large object. Okay? Now, the only force on little m is gravity. So gravity pulls this direction. That's the force of gravity. But it's moving perpendicular to that. So this is its velocity, v. And so gravity makes it move in a circle. And so we get the result that the force of gravity must be exactly equal to the centripetal force if it's moving in a circle. Okay? That leads us to the result that the force of gravity, which is g, the mass of this object, times the mass of the little object, divided by the radius of the orbit squared. So that would be the distance from the center of this object to the center of that object. That gravity force must exactly equal mv squared over r. The little m's cancel, so this mass doesn't matter. One of the r's cancel, and you're left with the result that g times the mass of the object divided by the radius of the orbit equals v squared. Okay? Another way to write that is this. We can say that if I take the square root of both sides, the velocity, which is what you get on this side, is proportional to 1 over the square root of the radius of the orbit. So take the square root of both sides here, and you'll get the velocity equals the square root of this side. So g and m are constants, they don't change. So the velocity is proportional to 1 over the square root of the radius. And this is an important relationship. If an object is orbiting another object, making the radius of the orbit bigger makes the velocity smaller. In fact, if I were to make the radius of the object 9 times bigger, then the velocity would get the square root of 9, or 3 times smaller. Okay, you would need to move slower to orbit at a farther distance. So the AP likes to ask questions about that relationship. If you go back to here, though, you can also write it as g, big M, divided by r. The velocity of the object moving in a circle is equal to its distance, which is 2 pi times the radius, divided by the time it takes to go around once. So the velocity is distance divided by time, and of course this is squared, right? Because v squared. This gives you Newton's result, which is also Kepler's third law. If I square the right-hand side and then cross multiply, I get g capital M t squared equals 4 pi squared r cubed, which you can look at as saying basically that the period squared is proportional to the radius cubed. Okay? And that was Kepler's law. I'm kind of off my page here. So there you go. The period squared is proportional to the radius cubed. Okay? So there you go. There's a flying summary of everything we've done this unit on one page. And you're going to solve some problems to kind of review these ideas. And I've got a AP Classroom set of multiple choice questions to kind of practice. And we will have our test tomorrow on this. Okay? So work through it and let me know how I can help you.